Okay, I'm going to begin section 2.5 now, which is the topic of continuity. We've already been using continuity a little bit, although we're going to be more clear about that term now. Definition: a function f is continuous at a number a if three things happen. F of a exists, that is, a has to be in the domain of f, okay, like you can't have a hole in the graph or a vertical asymptote or something like that. The number has to be in the domain. Item 2, the limit as x approaches a of f of x exists. We've seen limits that don't exist, okay, so the limit has to exist. And then item 3 says that if these two things exist, they have to be equal to each other. Okay, the limit as x approaches a of f of x is the same as f of a, right? I want you to put a star by that last item there, item 3, and make sure that you know that, okay? Because any questions about continuity that they're asking you for, where they want a calculation to be there, they're wanting you to use this starred statement, okay? And using that, we will be able to show that a function is continuous at a number a. We say that a function is continuous if it is continuous at every number in its domain. Okay. Here'd be some examples of non-continuous functions. In the first example, f of a does not exist. Okay, and same thing with this second example too. F of a does not exist. So you can't have a hole in the graph or a vertical asymptote. A has to be in the domain of f. Okay, here's another example of a discontinuity. Now f of a exists, right? Here'd be that point, f of a. But the limit as x approaches a of f of x does not exist. Okay, like the as I'm selecting values around a, getting closer and closer to a on either side, the y values are not approaching the same spot there. Another example. Okay, so in this problem, f of a exists. That'd be this point right here. The limit as x approaches a of f of x exists, since you're approaching the same y value on either side of a. But these two things are not the same, right? F of a is up here on the y-axis. The limit as x approaches a of f of x is right here on the y-axis. Those are not the same number. They're not equal, so we'd have a discontinuity. Now, a very easy way to describe continuity to somebody is basically saying that you have a situation where you can graph a curve without lifting your pencil from the paper. Okay, anytime you've got to lift the pencil from the paper, there's going to be a discontinuity. Okay, now let's take a look at a definition here. A function f is continuous on a closed interval ab if it is continuous on the open interval ab, and the limit as x approaches a from the right of f of x is f of a, and the limit as x approaches b from the left of f of x is f of b. Okay, so in other words, you're closing in the endpoints here with these two equations, these two statements. Let's take a look at an example of using this here. So in this example, I want us to show that the function f of x, which is the square root of 1 minus x squared, is continuous on the interval -1 to 1, okay, in the closed interval. By the way, the domain of this function here would be the set of all x such that x is between -1 and 1, including the endpoints. I know that I don't want the square root of a negative, right, because that would not be a real number. So 1 minus x squared, I'd want to set that to be greater than or equal to 0, since I don't want that to be a negative, and then solve this inequality for x. Okay, well, x being between 1 and -1, including the endpoints, would be the solution then to this inequality, and that would be the domain of the function. So ultimately in this problem, we want to show that the function is continuous on its domain. Okay, does anybody know what this function looks like if we were to draw it? Yes, this should be a circle, or part of a circle, right? It's not going to be a complete circle because a complete circle would fail the vertical line test. Now, if I had the equation x squared plus y squared equal 1, that would be a circle centered at the origin with a radius of 1. Okay, now if I were to solve this equation for y, subtract x squared from both sides and then take the square root of both sides, of course don't forget about the plus or minus, then here would be the equation rewritten into a form where I've solved for y. Okay, we call that explicit form. I'll talk about implicit form and explicit form in the next chapter in one of the sections. Now, I don't have a plus minus here. I've only got the plus case. So what that means to us is we are only working with the top half of the circle. Y equals negative the square root of 1 minus x squared would be the bottom half of the circle. Okay, now of course to use function notation, you have to have a function. You have to have something that will pass the vertical line test. A complete circle would fail that vertical line test, so I'm only working with the top half of the circle. Okay. Now, when I draw this, it appears that f is continuous on the interval -1 to 1, since we didn't have to lift the pencil from the paper. Now, that's not really a mathematical argument. Okay, you can't really reason with somebody by saying, well, I drew the picture and I didn't lift my pencil from the paper. Okay, like that's not really a convincing way to argument to somebody. Okay, so we'd want to give a more of a mathematical reasoning behind this, and so that's what I'm going to do next. Okay, I'm going to first show that f is continuous on the open interval -1 to 1, and then we'll show that it's continuous on the closed interval -1 to 1 by closing up the endpoints there. Okay, and I'll be using the definition of continuity. Okay, that's this starred statement right here. All right, so, well, let's see. So if I let a be some number between -1 and 1, then I want to show that the function is continuous on the open interval. So I need to show that the limit as x approaches a of f of x and f of a are the same thing, okay? Because that's what the definition says. That's what this starred statement says. And again, I want to emphasize that whenever you're asked a question about continuity, first thing, always think of this starred statement, okay? So that's what I'm doing. Now, f of x is the square root of 1 minus x squared, right? And the limit as x approaches a of the square root of 1 minus x squared. Well, I can distribute the limit notation underneath the radical and then also into the two terms here, right? Limit of a difference is the difference in the limits. And the limit of a constant is always the constant. The limit of a power function is where you can just apply a direct substitution for your a value there. And of course, lose the limit notation, right? Now the square root of 1 minus a squared, that would be this function here, but when you've plugged in a. Well, that's what I had to get to, right? I had to show that the limit as x approaches a of f of x and f of a were the same thing. I've just done that, okay? So thus, f is continuous on the open interval -1 to 1. Okay, now the next thing I'm going to do is I'm going to show that the endpoints would be closed circles. Okay, and of course I can see that on this graph here, but I need to show that, by using the definition for continuity. Now the limit as x approaches -1 from the right of the square root of 1 minus x squared would be 0. The fact that I'm approaching from the right is not relevant. I can make a direct substitution since -1 is in the domain of the function. Also, f of -1 would be 0, right? If I plug in -1 here, I also get 0. Okay, so I'm getting the same number there. Also, the limit as x approaches 1 from the left of f of x is 0. Again, I can make a direct substitution. Doesn't matter that I'm approaching from the left. And f of 1 is 0. Okay, if I plug 1 into the function, I also get 0 here. Now, I need to be approaching 1 from the left, right, because I don't have any graph on the right side of 1. So the notation here would be important. Okay, I'd want to write a one-sided limit. Okay, I can't, and like for here, I'm approaching -1 from the right. There is no graph on the left side. Okay, thus, f is continuous on the closed interval -1 to 1. Okay, because we've shown that the function is continuous here at the single value -1 and +1. Okay, from these two calculations. Now, question: why didn't I just write like right here? Let a be between 1 and -1, including 1 and -1. Like, why not do that, and then we can just conclude that the function is continuous on the closed interval -1 to 1. Like, why do this extra thing here? Well, I mentioned just a moment ago that the direction is important. We have to look at this as a one-sided limit. On this picture here, okay, like I don't have any graph on the left side of -1. I need to indicate that I'm approaching from the right side. If I didn't write that, if I just said limit as x approaches -1 of the square root of 1 minus x squared, that would be something that does not exist. Remember, the idea of a limit is that you have to be approaching the same y value on either side of x, either side of x. Well, I have a graph on the right side of -1, but I have no graph on the left side of -1. So that limit would not exist. Okay, it's a notational thing. So basically, I'm saying that the way that I did the problem here, by first showing that it was continuous on the open interval and then closing up the endpoints, that is my only option. I can't just do the whole thing all at once because I don't have, a graph showing on the left side of -1 or anything on the right side of +1. There is a start-stop thing going on here. Let's take a look at another example. Okay, determine where the function f of x is discontinuous. I've got a piecewise function here, and I've sketched the graph. So y equal 2 to the x is an exponential. Okay, of course, there's a horizontal asymptote there on the x-axis. The curve is rising. If x is 0, anything with 0 power is 1, right? So the curve would pass through the point 0, 1, and then shoot upward and outward in quadrant 1. I don't want that entire curve to be showing, though. I only want the part for when x is less than 0. Okay, so if I did draw the entire curve for y equal 2 to the x, I would erase everywhere that is 0 or bigger. Piece 1 is done. Okay, so piece 2, -1 if x equals 0. Well, that's essentially telling me plot the point 0, -1. You had a horizontal line at y equal -1, but we don't want that whole thing. We only want the single point for when x is 0. Okay, and then piece 3, y equal cosine x. So we know the cosine curve, right, oscillates between 1 and -1, but I don't want that entire curve to be showing. I only want the part for when x is greater than 0. Okay, so anything that I would have drawn that is 0 or less, I would have had to erase there. All right, so here's a quick sketch then of the graph of f of x. Where is f of x discontinuous? Well, I can see from the picture that in order to draw this completely, I would have to lift the pencil at 0. Okay, so f is going to be discontinuous at 0. Now, I would not want to say because I had to lift my pencil. That's not a convincing mathematical argument. Okay, you have to use the definition for continuity. Again, that's this starred statement here. So I'm going to use that next. Okay, the limit as x approaches 0 of f of x would be 1. If I'm on either side of 0, the y values are getting closer and closer to 1. And f of 0 would be -1, right? If you'd be using piece 2 there. 1 does not equal -1, right? And in the starred statement, I have to have these two items be equal to each other. I'm not seeing that in this problem. 1 does not equal -1, so therefore you're going to have a discontinuity at x equals 0. Here's another one. Okay, how about what if we had g of x equal, here's another piecewise definition. Okay, and I'm going to find the following here. Now, I could sketch a graph if I want. I don't need a graph, okay? Like, I didn't need a graph for this problem. Graph is helpful, okay? But I'm still going to be applying the definition for continuity, okay? It's all about that starred statement there. So in part A, I want to find the limit as x approaches -2 from the right of g of x. Well, if I'm on the right side of -2, that means I'm going to be using piece 2, right? X is greater than or equal to -2. So where I see, the function inside the limit, I've more specifically written piece 2 there. And I can make a direct substitution of -2. The fact that I'm approaching from the right is not relevant, okay, since I can directly substitute, and the square root of 0 is 0, then the answer is 0 there for part A. Okay, how about part B? The limit as x approaches -2 from the left of g of x. Well, if I'm on the left side of -2, that means I'm using piece 1, right? Because x is less than -2 there. So where I see the function inside the limit, I'm going to replace that with piece 1. And again, I can make a direct substitution and lose the limit notation, okay, because -2 is in the domain here. -2 to the 5th would be -32 plus 3 is -29. Okay, part C, the limit as x approaches -2 of g of x, that does not exist. Since the limit as x approaches -2 from the right of g of x and the limit as x approaches -2 from the left of g of x are not the same thing. Okay, it depends on what side of -2 you're on. Part D, g of -2. Well, if you're using -2 and plugging in that number, you got to use piece 2 here, right? X is greater than or equal to -2. So I would just plug in -2 into piece 2 there, and I get the square root of 0 is 0. Okay, is g continuous at x equal -2? No. There's lots of conclusions that you can make about this, explanations rather. One explanation would be to say that the limit as x approaches -2 of g of x does not exist, right? In talking about continuity, the limit as x approaches a of f of x has to exist. Another explanation that you could give is to use the starred statement. You could say that, since the limit as x approaches -2 of g of x is not equal to g of -2. Okay, either one of those two explanations I would be fine with. Okay, but make sure that you are giving an explanation. Okay, they will ask you to do that, and again, you want to be using the definition for continuity in that.